Hello, my name is Jakub and I would like to talk about the project I did here at the University of Edinburgh for the summer of HPC 2018. This project is a part of Environmental Monitoring Baseline, which is a system that aims to provide a reliable framework for real-time data analysis of environmental sensors that are located around the UK. I would like to talk about the main components of the system and illustrate them using some diagrams. The first component is KAFKA. KAFKA is a communicating server that allows to pass information across various applications and services via a single zookeeper server. Zookeeper server ensures that the messages are synchronized so we always know where they came from and when they came. KAFKA operates on a simple basis of producers and consumers. Producers are the applications that put the data in so-called topics, and consumers are the applications that retrieve the data from those topics. In this diagram, we see that KAFKA producer puts the data into the three topics A, B, and C. These messages from various topics are synchronized by a zookeeper instance, so that when a consumer wants to retrieve the data from, let's say, topic B, we are certain that the received messages will come in the correct order. However, passing multiple messages from multiple topics in KAFKA is very messy. Each of the topics might contain messages in a different format. So how can we ensure that the consumers know how to parse the data correctly? For that, we actually use the schemas. Schemas are the structures that describe our data. So this chunk of code illustrates the actual schema that is used as a database input. For example, if we see a field named timestamp start of type string, that is a message for KAFKA consumer to parse the data that has been placed in that field as a type of string. In this use case, we see as previously a KAFKA producer and a KAFKA consumer. However, this time KAFKA consumer will ask the schema registry for a proper schema in order to parse the data that has been fetched from the topic A. In such a situation, further processing has been made easier, since we are sure that the data provided by KAFKA consumer is in correct format. To store our environmental data, we use the Cassandra database. It is a distributed NoSQL database and it operates using multiple nodes. The distribution of the data provides reliability and a higher throughput for real-time data processing. In this diagram, we see a Cassandra database composed of 4 nodes, A, B, C, and D. Each cluster of nodes has its own node coordinator, and in this case that's a node D. That node D serves as a means of communication between the client side and the other nodes. For example, if we issue a query, the node D will locate the chunk of data that we are interested in on one of the nodes and return it to us. Because it is a distributed database, each node contains just a tiny fraction of the whole dataset. Containers like Singularity provide a way of separating our applications from the resources and applications running directly on a host operating system. By using the containers, we improve in security, since a fatal failure in one of our container applications will not interfere or affect our main operating system. Here we see that unlike in virtual machines, containers do not emulate a guest operating system, but instead they provide a daemon process to help the container communication. In opposition to Docker, another popular container service, Singularity does not require root privilege to run, and also does not completely isolate the host namespace from the container namespace. On the contrary, Singularity allows the host processes and container processes to interact with each other. Furthermore, Singularity container can also access the root file system. In EMB project, we use Spark to create a processing code that detects anomalies in any time of real-time data. This requires also an additional resource manager that is called Yarn. Yarn manages the resources directly on HPC's file system called Lustre. In the blue circle, we see the representation of container swarm, that is, multiple containers that can submit and load files to Spark master context. For example, every 3 days, a Kafka consumer would launch a job asking Spark to find anomalies in the last 3 days. The Spark master actually has the parallel code, but the code is managed and executed by Yarn, the resource manager that allocates the jobs to node managers. As I have mentioned before, in this project we are interested in the anomalies. To find anomalies, we use the seasonal trend decomposition algorithm, in particular a more advanced version developed by Twitter. It is a statistical learning algorithm that allows for extraction of patterns, trends, and anomalies. In this example, I have decomposed Amazon stock prices into the 3 constituents. The trend on the top, which depicts a general pattern of the data, the seasonal on the very bottom that extracts the periodicity of the data, here we can see a yearly fashion that occurs, and the residual component, which is a leftover of the latter 2, and here is where we look for the anomalies. Here we see the overview of the whole processing system. What is worth noticing is that the environmental data is stored via EMB topic to Cassandra database. However, sometimes Kafka producer launches a Spark job to detect anomalies in a specified period. Spark would then fetch the data from the database, process it, and store the found anomalies back into the database. Thank you for watching this video. That's all for today.